Okay, well, maybe we should start. I want to thank you all for coming to our 9th lecture of a series of radio astronomy talks that we've been holding this year. Before we start, I'd like to thank George Halburn, the late George Halburn, for his support, generous support that he provided. And without his support, we would have not been able to really have this series of radio astronomy talks. We've also been supported by Sierra, the College of Arts and Sciences, and also our own department. Today we're pleased to have Lucy Ziurys from the University of Arizona. She is a professor of astronomy and chemistry. She has this joint appointment at the university, and she teaches both classes actually in astronomy and chemistry. She went to Rice University and got her BA, I think, and then she went to Berkeley in, I think, physical chemistry department and got her PhD. The year, should I say?
Oh, we don't want to talk about
No, okay, all right, so okay, forget about that.
some place in the past.
Yeah, right, in the past, right. And she's currently the director of Radio Astronomy Observatory, where they have 2 different telescopes, big, really very, very big radio telescopes at the University of Arizona. It just belongs to the university alone. So 2 major radio telescopes. Lucy's primary research is focused in understanding of the gas chemistry in interstellar space. She also does a lot of research in molecular spectroscopy, where she actually makes molecules and finds molecular line transitions. And then she uses these lines to discover molecules in space, these transitions that she actually makes in the lab. And she has discovered numerous molecules over her career. And hopefully she'll talk about some of these molecules. She applies millimeter wave devices for astronomical and laboratory applications. Because of her contribution to the field of molecular spectroscopy, she has really been awarded many awards and honors. And just to name a few is, let me just give you a few of her awards. She was a DAAD fellow at Max Planck Institute for Radio Astronomy. I don't know what that means. Okay. Yeah.
It's a German equivalent of the Fulbright Foundation.
Oh, okay, good. Zanta International, Emilia Earhart fellow. She was NSF Presidential Young Investigator Award. She had a NSF Presidential Young Investigator Award. She was also awarded NSF Presidential Faculty Award. She also was awarded NSF Creativity Award. Any other awards from NSF, Lucy?
No, I think that's it.
Okay, that's it. Okay. I just don't want to miss anything. Then also Annie J. Cannon Special Commendation Honor Award to distinction in undergraduate teaching in chemistry. Elizabeth and Keith Hedge Galileo Circle Fellow, APS Fellow, and in 2015 she received Barbara Max Stark Prize in Molecular Spectroscopy. So today she's going to talk about our increasingly molecular universe as revealed by radio astronomy and laboratory spectroscopy. And so I just want to mention also that these talks that we have all been audio taped. If you'd like to listen to them, please go to can you just go one slide before? So I have the website. If you'd like to actually listen to all the previous talks that we've had, you can always listen to them. And we'll have also this talk audio taped, and you can enjoy listening to them if you miss these talks. So without any further ado, please take it away, Lucy. Thanks.
Thank you. Well, thank you very much for inviting me. It's always interesting to talk to an audience like you about my favorite topic, which is interstellar molecules. I can't possibly cover everything, but hopefully you'll get some gist of what it's like to study molecules out in interstellar space. And so my title focuses on the molecular universe. And you might think astronomy, this deals with atoms, this deals with atoms that are ionized. And it is true that astronomers for centuries thought that interstellar space was the realm of atomic material. But it's radio, and in particular millimeter wave astronomy, that really changed this paradigm. And this began in the 1970s with the discovery of CO, carbon monoxide, in its 1 to 0 transition. And this was work done by Penzias, Bob Wilson, and collaborators. And they actually pointed a radio telescope towards the Orion Nebula, that's in this sort of Orion, and they measured the first spectrum of carbon monoxide. And this is what their spectrum looked like. It's rather primitive for what we can do now, but it was a major breakthrough because all of a sudden people realized that there might be molecules out in space. And this discovery was quickly followed by discoveries of a whole lot of other molecules. Some of the list is here. There are many of the early pioneers who were involved in this, such as Penzias Wilson, Pat Thaddeus, Charles Towns, Jack Welch, Phil Solomon, and so forth. And now, when we think of, for example, our galaxy or many external galaxies, we often think of this optical picture. This is a picture of our Milky Way, and you can see all the stars and the dark dust lanes. But if one had eyes that could see molecules, this is what it would look like. And what we're seeing here is a contour map of emission from carbon monoxide in the 1 to 0 rotational transition. And the color contours just show us the intensity of this transition. But you can see that CO is found throughout our galaxy and even in interesting places outside our galactic plane. And so our view of the universe has dramatically changed. In fact, I think now it's considered that in about the maybe 10 inner kiloparsecs of our galaxy, it's about 50% molecular in nature, as opposed to atomic. And of course, molecules are also seen in external galaxies, and here we're looking at a spiral galaxy, and the contours again show the distribution of carbon monoxide. But there are more molecules out there than carbon monoxide, and this kind of shows, perhaps it's not completely up to date, but it's pretty much up to date, of the known interstellar molecules. So we've gone from CO to detecting a wide range of species. Many species contain carbon, and we see a lot of common laboratory things like ethanol, dimethyl ether. And we see some unusual species that have these carbon chains and some carbon chain radicals. We also find species with silicon, with metals in the chemist sense, potassium, magnesium, and so forth. And more recently, we've been finding species that also contain phosphorus. And you can see from this list that a lot of these species, about half of them, are quite unusual species. There are things that are molecular ions, like N2H+, that's protonated N2O, protonated CO, protonated formaldehyde, and some of these strange carbon chains with a lot of carbon, C6H, C7H. And very recently, we've expanded what's been detected to C60 and C60+. So we're beginning to see a lot more complicated species. And about 90% of these molecules have been detected by radio astronomy. So this is really the realm of the radio astronomers. So how do we know what molecules are out there? If we look at this list, you might say, well, astronomers, sometimes their data is a little questionable. But really, every molecule on that list, I believe, is an absolute and secure identification. This is because we use quantum mechanics to detect these molecules. Typical molecular gas is cold and dense by interstellar standards. Cold meaning about 10 to 50 degrees Kelvin. Density is on the order of 10 to the third to 10 to the sixth particles per cc. And why that seems dense by interstellar standards, it's quite diffuse by laboratory standards, because 10 to the sixth particles per cc at 10 Kelvin is about 10 to the minus 12 torr. So you're really looking at very diffuse gas, but it's just dense by interstellar standards. And so what this means is that, you don't have a lot of collisions, you have a lot of time, and you're down at 10 to 50 Kelvin. And so if you look at an energy level diagram of a molecule, one recognizes you have electronic wells that involve transitions between different electronic states. Those are the high energy ones. We have vibrational levels. which sort of lie in the infrared, and then the lowest energy levels, the lowest energy transitions are in the rotational regime. So a molecule simply rotates and it has quantized energy levels, and that rotation depends on the molecule's moment of inertia, which is simply mu r squared, where mu is the reduced mass for a simple diatomic. Of course, these equations get more complicated as the number of atoms increase. And the moment of inertia is simply proportional to what we call a rotational constant, and these energy levels then are, in the end, inversely proportional to the moment of inertia. And it just turns out that the moment of inertia, most simple interstellar molecules, puts their rotational transitions at millimeter wavelengths. And this is why millimeter astronomy has been so successful in furthering the field of molecular radio astronomy. And so what happens then is that we have collisions. The most common interstellar molecule is H2, so basically collisions with H2 knock the molecules up to a higher rotational level, followed by spontaneous decay, and we create emission lines, which we detect with radio telescopes. And this is all done in the gas phase, okay? So we're studying rotational spectroscopy, doing rotational spectroscopy halfway across the galaxy. And so one detects these emission signals with radio telescopes. I'm sure you've heard a lot about radio telescopes in the course of this series, but we're typically measuring emission spectra. And we detect these spectra with what we call heterodyne receivers. And that's the detection element on these radio telescopes. And what you see here is a picture of the University of Arizona's telescope, the sub-millimeter telescope on Mount Graham, and the 12-meter on Kitt Peak, which recently was replaced with one of the ALMA prototype antennas, which was located in New Mexico. We moved it and got it working, and now it sits in the dome of the former 12-meter, and it's almost done with its first full observing season. Anyway, back to heterodyne receivers. What do they consist of? Well, very basically, we get signals from the sky, which are collected with the dish, and then they're focused into the detector system, and we mix what we call a local oscillator signal with the sky signal in what we call a mixer. They're typically what we call SIS mixers, superconducting, insulator, superconducting, and we beat down to a lower frequency and intermediate frequency, which we quickly amplify with a very low noise amplifier. And this frequency difference is sent to a spectrometer backend, which breaks up the signal as a function of frequency, and we create a spectrum all at once. And so this is like a typical interstellar spectrum. This is the CN radical, and the red trace is what we observed with the sub-millimeter telescope, for example. It's the 2-to-1 rotational transition. Spectroscopists like to always confuse other scientists with their quantum numbers, so now we use N, but anyway. And what you're seeing here is the hyperfine structure due to the nitrogen spin of I equals 1. And the blue trace underneath these spectra are the laboratory measurements. So we have laboratory measurements on the CN radical. We can take them to a radio telescope, and if the signals are completely duplicated, we know that this molecule, for example, the CN radical, is present in this particular molecular cloud, and we know for sure, okay, in the simplest sense.
Can I ask a question?
Sure.
So are there any of these molecular lines that are coming from the stars themselves, or is that signal just way too weak? And
we see signals coming from circumstellar envelopes, which I'll talk about in a moment. Okay. We get radio signals from molecules from a lot of different types of sources. Okay, so one can think of a radio telescope as a molecular spectrometer with 4 basic parts. You have the dish, which collects the signal. And by the way, these dishes for millimeter work have to be pretty accurate. For example, the sub-millimeter telescope, which is a 10-meter dish, which is what's shown here, has a 15-micron RMS surface accuracy across the whole 10 meters. Okay? And they consist of panels which are adjusted. And then you have some of the heterodyne detector system, which is fairly complicated and detailed electronics, which I won't go into. And then we have some kind of spectrometer backend. In this case, you're looking at the filter bank system that we have at the sub-millimeter telescope. And these sort of backends, we call them backends, have the multiplex advantage in the sense that you take signals and you don't have to scan in frequency. You get a whole bandwidth of frequencies instantaneously. And then, of course, everything has to be run by some kind of computer control to coordinate the data collection with the signal processing. And for example, at the sub-millimeter telescope, we have 25 separate computers all talking to each other in order for us to take data.
Are you saying these filter banks are analog devices? Or?
These in particular are analog devices. We also have digital backends as well. I just had this picture available. And then what kind of spectrum do you get? Well, one often thinks of astronomy as producing things that have to be reduced. But for example, this is just a raw spectrum. Taken with one of our telescopes, we're looking towards a molecular cloud in the galactic center known as Sagittarius B2 North. I'll talk more about it later. This is 5 hours of signal averaging, I must say. But you can see the individual lines. It's pretty clear where the signals are and the noise are. And we can measure every single pixel here is about 1 megahertz. And so, we can get a center of a line to half a megahertz very easily. And so we can measure the frequencies and compare them with laboratory work.
You may want to say what the velocity is for the half a megahertz velocity resolution.
0.65 kilometers per second. Okay, actually this is 195 kilohertz to be exactly honest. But so, you can pick, your different backends have different kind of resolution. So you can, tune your resolution to the width of a line you expect to observe as well. However, not all spectra are that simple. Here's more typically of what we see towards many types of molecular sources, in particular these clouds that exist throughout the galaxy. So here's a spectrum. This is a typical spectrum towards the Sagittarius B2 North cloud. And this is maybe several hours of signal averaging integration. And you can see we've identified a lot of the molecules, and there are a lot of these organic type species, methylformate, ethyl cyanide, dimethyl ether, and so forth. But you see a lot of features we've labeled U because they're unidentified. We don't know what they are. This is the noise level right there. Give you feel.
For a spectrum like this, is the width of the peak given by some sort of turbulence or motion?
Yes, it's by the Doppler motions of the source. Okay, so some sources are colder and have less turbulent or other sorts of motion, so the lines are narrower. This is a region of star formation, so there is some motion. And so the lines typically here are 10 to 20 kilometers per second wide, if that means
anything. So the
anything.
instrument itself doesn't contribute to the width at all?
For the most part, no, because the line widths are broader than the instrumental resolution. Okay, so it's obvious from the spectrum that if we want to start identifying some of these unidentified features, we have to do laboratory work. So I'm going to talk a little bit about the sort of laboratory work that I do in my lab and what other people do with similar sorts of scientific ambitions. So we're talking here about gas phase rotational laboratory spectroscopy, which typically has a accuracy of about 1 part in 10 to the 7, 10 to the 8th. Okay, so this is pretty accurate stuff. So you're able to resolve things we see in molecules like fine structure and hyperfine splittings with this sort of resolution. And this is useful because usually hyperfine and fine structure gives you a nice pattern for a given molecule, which is really good in identifying it out in interstellar space, besides the harmonic pattern generated by the rotational levels. And so we typically use 2 types of spectroscopy, and this is pretty much the norm for this type of work. One type is millimeter, submillimeter, millimeter terahertz direct absorption spectroscopy, and it's more in the what we call the millimeter terahertz range. And it has a very basic design. You create a molecule in a gas in a cell. You have some source of millimeter wave radiation. You scan it in frequency, and you monitor the absorption by the molecule in the cell with a detector, and thus you measure various rotational transitions. But that's sort of the basic picture. In principle, they're much more complicated. We have complicated phase locking electronics to stabilize the source. And we do things like phase-sensitive detection, but I won't go into the details. But in reality, it's more complicated than that. But it's still direct absorption. We also use a time technique, pulsed Fourier transform microwave, and we've pushed it up to millimeter wave wavelength spectroscopy. We operate from 4 to 90. Typically, people operate 4 to maybe 40 gigahertz. And this is a different sort of spectroscopy. It's done in the time domain. It's very similar to nuclear magnetic resonance spectroscopy. And in direct absorption, you scan your source and frequency. Here you collect signals with an instantaneous bandwidth of about 1 megahertz. And you do this sort of thing in a Fabry-Perot cavity. So you have 2 mirrors, very nice surface, highly refined mirrors with nice surfaces, highly refined surfaces. And you pulse your molecules in some kind of supersonic expansion. Fractions of a second later, you'll pulse or microwaves in at a given frequency, which has about a megahertz bandwidth. And of course, it's a Fabry-Perot cavity. We typically have a high Q factor such that you maybe get 100, the signals bounce back between the two mirrors 100 times and interact with the molecules coming out of the jet expansion. And the molecules absorb if there's a transition within that particular frequency. And then they emit with time. And we collect their signal as a function of time, so it's emission spectroscopy. We collect what is known as the free induction decay, and then we do the Fourier transform of that and get a spectrum. So that's the other type of spectroscopy we do. And of course, this is all based on some kind of frequency synthesizer, so you'll take data at one frequency, data at another frequency, and optimize the cavity as you move along. None of these systems are commercially available. If you want to do this sort of spectroscopy, you build them yourself, or your graduate students build them.
So it was a supersonic beam going through the cavity, right?
Yes.
And you're taking a spectrum for how many microseconds? I didn't see the x-axis.
For here.
The previous one, I think.
Oh, gee.
I was just curious if it's the same molecules that are giving you that entire time sequence, or if you have to do.
This is microseconds. Okay,
So
so we're up to 300 microseconds, and so we're pulsing that valve at 10 times 10 hertz. So we do this experiment 10 times a second, and then we just signal average. Okay.
But then they stay. Each batch of molecules stays inside the cavity for that full 200 microseconds.
It takes a little bit of travel time from the nozzle to the center of the cavity, so maybe about 300 microseconds they stay in an optimal region to interact with the microwave radiation. Okay.
Transverse or axial?
Okay, well, they do both. We actually do ours. I'll show you in a second. Some people shoot it perpendicular. Some people actually put the nozzle in the mirror. We have an angle approach. We didn't want to put our nozzle in the mirror.
Longer that way.
Sorry?
Would they hang around longer?
Yes, and so you have to optimize your machine. You have to do experiments to get the optimal timing. Okay. Okay. So, I mean, just to give you a feel for what these things look like, here's one of my direct absorption spectrometers. It's a single pass system. So you have your frequency source, where we use a gun oscillator, a solid state oscillator, with a Schottky diode multiplier. It's all waveguide, and then it's launched quasi-optically into the cavity. Reaction cell, about a meter long gas cell in this case. We run an AC discharge along the length of it to create unusual molecules. In this case, we had a phosphorus source, which we developed to vaporize phosphorus. And then we have our detectors, which are typically helium-cooled indium timidide hot electron bolometers. They're incoherent devices, and they just detect basically the change in heat at a very basic sense due to the microwaves. That's what it looks like all together.
Environmental gas, so you can maintain a plasma? Or?
We will actually do a mixture and put it in the cell. So typically we operate at pressures on the order of 100 millitorr total pressure. Okay, so we want to keep the pressures down because of pressure broadening, wrecks our resolution. Anyway, this is our cell here. You can see we're running a discharge, and there's a big pumping system and our source and our detectors at the other end. Just another one of our spectrometers. The cell in this case is a double pass system, so we have a grid here to separate out incoming and outgoing radiation. You can see our microwave source here, the detector, double Dewar system because we have to cool with the liquid helium temperatures. Pumping system, Roots blower, pumping system. Maximum displacement seems most important in making some of the molecules that we try to make rather than ultimate vacuum. Our Fourier transform microwave spectrometer here answers this question. So this is a block diagram of that. Here's the two mirrors for the Fabry-Perot cavity, and our beam comes in at a 40-degree angle. So we just sort of have it come right from behind the mirror. You actually gain in signal to noise by having it transverse as opposed to perpendicular. And this kind of arrangement is sort of the best of two worlds. And so we have two sets of mirrors. Here's a picture of our 20-inch mirrors where we embed little antennas which launch and detect the radiation within the cavity. And as I said, it operates at a 10 hertz rate. And so pulse the molecules in, pulse the microwaves, let them interact, wait, collect the signal, then pulse more molecules in, pulse the microwaves in, and so forth. And that's just a picture of it. It's a big vacuum chamber. And because we have to do this in a supersonic expansion, we've got to pump this down to about 10 to the minus 8 torr. And the backing pressure on the valves, a couple of atmospheres. And recently we've incorporated a laser into this system to do what we call laser ablation. That's a picture of one of our YAG lasers. And so I can talk all about the instrumentation, but the biggest limitation in all this type of spectroscopy is making the molecule. Most interstellar molecules that are detected today are unusual species that you don't find in bottles or gas cylinders. They're radicals, they're ions. You can't buy them. You have to make them in some kind of non-equilibrium condition. And so we have all these tricks employing AC and DC, glow discharges. Sometimes we use ovens to heat things up. Organometallic precursors if we're interested, for example, in molecules containing iron. And recently, as I said, we've used laser ablation coupled with a supersonic nozzle in our Fourier transform machine. So there's all these different tricks, and you just try things until something works. Things don't always work all the time. Okay, so just one more point about the experimental stuff. This is a sort of trouble we have to go to make some of these molecules. People typically have done laser ablation. Here's a block diagram of it. You have a pulsed valve, you have a rotating translating rod, you hit it with this YAG laser, about 300 millijoules per pulse. You ablate the metal, you shoot in your reactant gas from this nozzle, it mixes, and then it shoots out into the chamber, and hopefully you're going to make the radical you're interested in. And recently we've had to incorporate a DC discharge in addition to the laser ablation just to make some of these radicals. And we found out without the discharge, we don't make them. So the point here is that it's all very tricky, and a lot of it's trial and error. So, give you an example of how it really works. One molecule we've studied not too long ago was FeCN. We were very interested in iron because iron's like the holy grail of the metallic elements. It's rather abundant, about 10 to the minus 5 relative to hydrogen, which is abundant for a metallic element in the chemist's sense. And people had been finding metal-containing molecules out in interstellar space, usually bonded to the CN group. Not always bonded to the carbon, sometimes the nitrogen. And so we were very interested in making the molecule with an iron atom there. But the question is, for example, are we going to make FeCN or FeNC? Both of them might exist. They're metastable isomers, which is more stable. Are they going to be linear? You might think they're linear, but for example, sodium cyanide is T-shaped. So there's a structure problem. Then we have the question of what is the ground electronic state? Now, I'm not going to explain all these weird molecular term symbols, but we didn't know if we had 5 unpaired electrons or 3 unpaired electrons, and that would influence how our spectrum looked. So there was sort of a project I kept giving to one graduate student after another over a period of 10 years, and finally I had a really good student, and he got very interested in doing this project, and he actually found the molecule in the laboratory.
You get all those valence states, magnesium 2, 1, 3 for magnesium, sodium, and aluminum.
Well, actually, this is magnesium, probably magnesium plus CN minus.
So they're ions?
No, they're neutrals. And actually, if you study their chemical bonding, which you can do by looking at some of the hyperfine structure, they've got a fair degree of covalent character. The one that's most ionic is sodium cyanide, which actually is sodium plus orbiting the CN minus group. That's why it's T-shaped on average.
So forget all the chemistry I learned, right?
Yeah, to some level. Not completely. Anyway, so this is the laboratory spectrum of one rotational transition between just two rotational levels, 50.5 and 51.5. And we get all these different lines because in this molecule we have spin-orbit coupling, and that gives us 4 spin-orbit components. And in addition, we have something called lambda doubling. I won't go into all the details, but this was a very nice spectrum. It took us a long time to find in the laboratory. And we found out the best way to make it was to discharge iron pentacarbonyl and cyanogen. And don't ask us how we got hold of cyanogen. So that's pretty poisonous. Okay, so this is the energy level diagram of this molecule then, and what you're seeing is one rotational, transition within each of the various spin orbit ladders, which we label by omega. And We measured many rotational transitions in these ladders, but we were never sure if it was FECN or FENC. So to make sure we have the right structure, we have to do an isotopic substitution. So we measured the spectrum of iron 13 CN. Carbon 12 is the normal isotope. And I had a very brave student that made carbon 13 substituted HCN. We used this as the reactant gas with this iron pentacarbonyl. We made it in a discharge. And then in addition, we also found what we found was the metastable isomer, FENC, but the signals were much, much weaker. So we're pretty sure that the iron bonded to the carbon is the ground, the lowest energy state of this molecule. And of course, you do all these measurements. Here are our lab measurements to, kilohertz of precision. And then what a spectroscopist will do, we'll fit it with some molecular Hamiltonian. And I won't go into the details, but you'll model all those interactions and come up with spectroscopic constants. And this was the grad student, Mike Flory, that did all this work. And just to confirm that we really had the molecule, before we went to look for it in space, we also measured the Fourier transform microwave spectrum. And so we went to even lower frequency. And it turns out that because of this unusual ground state, it is an inverted ground state. And if you think of Hund's rules, you'll recognize then that it's inverted because the valence electrons are more than half filled in the valence shell. So the omega equals 7/2 spin orbit ladder is the lowest. The lowest rotational transition is 7/2 to 9/2 right here. It's split by hyperfine structure due to the nitrogen spin of 1. And here's the Fourier transform microwave spectrum of this transition. And you see 3 lines there due to the 3 hyperfine components. And you have these unusual U-shaped profiles because of the beam expansion relative to the electric field in the Fabry-Perot cavity. But that confirmed it. And then we went to look for it in interstellar space, and we found it. And we found it in answer to someone else's question in an envelope of a star, IRC plus 10216, very famous. And because of an expanding envelope, the lines kind of have blocky line profiles, and you'll see the different rotational transition. We measured 5 in all, and that pretty much confirmed it. And we only looked for it in the lowest energy spin orbit ladder, and that was the work of my student, Lindsay Zach. So that sort of leads you through the process. So you can see it often can be long and involved, which just brings one interesting point about metal chemistry in interstellar space. We've found FECN. And here's a list of all the metal-containing molecules seen in the interstellar medium. And it's kind of interesting that the most common form of a metal in interstellar space is bonded to a cyanide group. Okay? This is chemistry that no one really understands. You also see some oxides and things with a halogen. Okay. So it's very interesting detecting new molecules and doing the lab work and getting to the telescope, and hopefully you'll find it in space. But there's much more to that in studying astrochemistry.
Can I ask one question before
Yeah.
you go? How did you know that these were the molecules you were interested in to begin with?
You don't. You make an intelligent guess.
So what was so you basically knew that you were looking for these, say, magnesium CN molecules to begin with?
Well,
Or somebody got lucky? Or
Someone got lucky and found sodium cyanide. Then it was like, oh, well, metal bonded into a CN group. We can try to make these in the lab. So we made them, and then we found more, and then we went on to iron. Sometimes you make things and you think they're going to be out there, and they're not.
Right.
And
The number of molecules is probably quite large. And so
Yes,
you
the
can't
number of
try-
molecules you could possibly measure in the lab is very large,
Right.
and
So-
especially when
so
you
do
start.
have any guidance from any sort of little toy models of what kind of molecules you expect?
There are some chemical models, and I probably should talk more about chemical modeling, but I'm not going to have time, and they sometimes predict that something might be there. And you might go on that. But half the time the models are wrong, so often it's what you can make in the lab. Governs some of it. And there's molecules we'd love to make, like ALH plus, that we haven't been able to make, but okay. Anyway, so I said, there's more to it than this, because molecules really are found in different types of sources. And one can actually tie this into a molecular life cycle, starting with stars and ending with planets. So what happens is that dying stars throw out their atmospheres, and this material flows away from the star, cools, and creates molecules. Eventually most stars completely shed all their atmosphere and form something called planetary nebulae. And these sort of objects populate the diffuse interstellar medium with about 80% of the material, and molecules are found here. They form what we call diffuse clouds, which collapse into dense clouds, which collapse into star-forming regions and protoplanetary disks and form planets, and then the cycle starts again. Some of this material, as I'll mention a little bit later, probably ends up on planet surfaces through exogenous delivery from comets, meteorites, and so forth. So what's perhaps interesting about this life cycle is that for a long time, people didn't think molecules existed in planetary nebulae. And so you sort of had molecules in stars, and they all return to atoms. Molecules in clouds, everything's returned to atoms. But I think we're seeing that actually molecular material is transferred between these sources, and so you never go back to the atomic state, and so that means you can build up to greater chemical complexity. But anyway, planetary nebulae and certain types of stars were environments we didn't expect to see molecules, and I'll explain why in a moment. I mentioned that stars near the end of their lifetime become unstable, and they start converting helium into carbon, and they start losing their outer atmosphere and form an envelope, such as what we see here. And you can't really get an optical image of it because they're cold, but this is an infrared image of that star IRC plus 10216. As the material flows away, molecules and dust grains form. And there's a complicated and interesting chemistry, which I don't have time to go into. But a lot of stars, maybe 10% of them or a few percent of them, are far more massive than the average star, which goes through this sort of slow death. And they violently throw off their atmosphere because they basically have super bubbles which pop through the atmosphere, and you get violent mass loss with shocks. And so their envelopes are often asymmetric because you have a red outflow going one way and another bubble burst and through material in the other direction, convective cells bursting through the atmosphere. And even in these kind of violent environments, they're full of molecules. And so we actually, a few years ago, did a big chemical study of the envelope of this supergiant star. It's about 40 solar masses. The star is a tiny dot in the center, and what you see is this huge envelope about 10,000 times the Earth to sun distance. So this thing is huge. And it's full of molecular material, and one of the interesting things is one can look at the line profiles and actually see what's dynamically happening in this star. So this particular part of the line profile in an SO2 molecule of all things, we believe is tracing a red-shifted outflow, and you can see the asymmetry here, and the blue part is tracing a blue outflow. And there are other interesting stars of this type like NML Cygnus, another supergiant star. And perhaps the most interesting thing is we've done what we call spectral surveys of these sorts of objects. So we measure all the spectral lines across a very large frequency range, in this case from about 210 gigahertz to 285 gigahertz. It's what we call the 1 millimeter atmospheric window. It's a region of the atmosphere we can see through. And this is, I won't go into the details here, but this is the spectrum of VY Canis Majoris, which is that supergiant star, and it has a lot of molecular lines. Not as much as this what we call an AGB star, one of the more common stars. They have far more lines, and you can see the difference. But we also did a survey of this supergiant NML Sig, and what I find striking here is that if you squint, it's like an identical spectrum. I mean, I'm just so surprised at this result. So.
Can I make sure I understand something?
Yes.
You're saying that you're getting these spectra from the stars, but it's not.
It's not. It's the envelope.
Themselves, it's the
the envelope. Yeah, it's the material lost from the star.
The star is way too hot.
Yes, but people do see molecules in some photospheres of stars, but that's optical transition high energy. Okay, we need the cooler material. Okay, here's another example of molecules found in strange environments, planetary nebulae. Now, if you look, people love to look at planetary nebulae because they have all these interesting shapes and colors, because basically we're looking at several atomic emission lines and they make some pretty pictures with them. Planetary nebulae is the final stage of the evolution of most stars. They last about 10,000 years, and this is where they basically blow off the rest of their material, and what's left is a white dwarf star in the center. It's about a half a solar mass that's left over, and all the rest of the material that was in this, part of which was in this circumstellar shell, is blown away from the star, and the white dwarf emits a lot of ultraviolet radiation, and it ionizes everything around it. And that's why you see these bright shells, and these are basically images in highly ionized atomic emission lines. And of course, because of all this ultraviolet radiation and these bright pictures one can see optically, it was thought that any molecules present from the previous stage would be photodissociated. And at least over a period of 10,000 years they should be. And this was what predicted by all chemical models. No molecules in these objects. We decided to have another look. And this is perhaps one advantage of having your own radio telescopes. So what we did was we picked about 17 different planetary nebulae. Here are pictures of them. Some of them are very little is known about, like this is K447. And we did a survey of 2 polyatomic molecules, HCO plus and HCN, via several rotational transitions. And we just had a look whether molecules were there. And that was some of the thesis work of my student Debbie Schmidt. And everywhere we looked, we usually found lines. So here are some HCN lines. You can see them there. Some of the profiles are a little bit contaminated by galactic emission. I won't get into that. But HCN, HCO plus lines. In fact, we detected HCN and HCO plus in about 75% of those sources. And then we found other molecules like the CCH radical, and what you see here is the doublet structure due to the spin rotation interaction. And we looked for even more molecules in select sources like M2-48. It's a middle-aged planetary nebula of about 5,000 years old. HCN, SO, SO2 even. Molecules are strong enough to see carbon-13 substituted species, which says something about the nucleosynthesis in the interior of the star, but I won't go into that, and even SIO. And of course, perhaps the most interesting object we studied was the Helix Nebula, which is about the oldest planetary nebula known. It's close by, it has a big extent on the sky, and so our telescope beam usually just looks at a little portion of the nebula. So we decided to pick 7 different positions and see if formaldehyde and HCO plus were there. Sure enough, every place we looked, both molecules were present. Then we looked at CCH and HCN, same thing, everywhere position we looked. Sorry, these spectra are a little. We found both molecules. I won't go into the details about the prime profiles. Eventually, we mapped the whole nebula in HCO plus, 200 spectra, and all around the sort of ring structure of the helix, HCO plus was present. So these molecules are present mixed in with this highly ionized atomic gas.
So how are the kinematics of these
Yes, this is a whole.
molecules different compared from ionized gas? Let's say.
Put it this way, we have far better spectral resolution, far better velocity resolution, and actually from this map we actually figured out what we think is a velocity structure of the helix. It's a bipolar nebula coming almost right on. And it agreed with some of the atomic data pretty closely when you looked at it. So you can use, if we do a map like this, you can determine the velocity structure. We had like 1.5 kilometer per second velocity resolution, and the best atomic study had like 15 kilometers per second. That's another story. Anyway, so in the end, we have studied enough nebula over enough age range to plot molecular abundances, and we always do this relative to H2 as a function of age. And you can see from this plot for the different molecules, these molecules get formed, or they're there from an early stage and they just stay, okay, to the very end of the planetary nebulae stage. And so what this means is that planetary nebulae, their ejecta form like 80% of the material in the interstellar medium. But it's not just atomic. These objects are ejecting molecules out into the diffuse interstellar medium. And so that's changes our way of viewing things. And the most interesting thing is Harvey List has done studies of similar sorts of molecules towards diffuse gas, and the densities are too low to see emissions lines, which is what we see. So he has to measure the absorption against a background quasar. And what he's seen so far is almost identical to the molecules the different chemical species we see in planetary nebula. And if one compares the abundances, one sees that the abundances drop by about an order of magnitude or 2 from the older planetary nebula into diffuse clouds. And so this is consistent with a picture that these molecules seen in diffuse clouds are just planetary nebula ejecta. They can't be formed in diffuse clouds by normal gas phase chemistry. So no one was able to account for them. Maybe you can account for diatomics, but not polyatomic molecules. And so I've basically said diffuse clouds are populated with remnant molecules. And we think what happens, and we know this from other studies, that the molecules form in clumps, and and so they're clumps full of gas and dust, and they're self-shielding, and so they get ejected into the diffuse interstellar medium, and they survive by a lot in part by self-shielding. So one says then, well, now we're jump-starting the chemistry in diffuse gas with molecular material. This sort of means that, over time, you don't always start with atoms, so you can really build towards greater chemical complexity than previously thought. And so one might ask, what is the limits of chemical complexity? And then we go to look at some of these denser clouds beyond stars, because they are really the sites of organic chemistry. And one of the big difficulties in understanding how complex molecules can get is how we identify them, which is with radio astronomy. Because complex molecules have complicated spectra. Hundreds of lines in the regions that we study them. And radio astronomy is not a lab. We have to observe the whole mixture as it stands. And so we have this problem of line confusion, which makes things very tricky. So some claims of molecules are in doubt occasionally. But to sort of approach this problem, we decided to measure a huge spectral range towards one cloud where we see hundreds and hundreds of lines, and then we can look at the more complicated species because we have maybe a couple hundred transitions to look at and see if the molecule's there. And that's more secure to look at 100 than 1 or 2. And so the cloud we studied was Sagittarius B2. This is a picture of our galactic center. Probably doesn't mean too much to you, but it's near the galactic center, very famous region. And over a period of about 10 years, we measured about 15,000 lines towards this one cloud in the 3, 2, and 1 millimeter atmospheric window. And this isn't noise, these are absorption lines. So I lied, we don't always have C emission lines. Anyway, it's a very complex project because we had to measure spectra in smaller spectral regions. That's about our typical measurement range, and then we just stitch them all together over a period of so many years. So if you blow up any one region, kind of looks like this. Once again, all these organic species, and U for unidentified. So what this survey has told us, and we're still analyzing it, sort of gives us a window on what's out there and what isn't, and we know for sure because we have many, many transitions to verify if a molecule is there in the data set. And so if one sort of looks at how complex the molecules are in SAGB2, this is a list of sort of the organic species we see, the more complicated ones. Alcohols, cyanides. Alcohols actually compose about 62.3% of the total carbon-containing material. But the most common species is something with the cyanide group, and we found 15 different species with the cyanide group. One also sees some simple sugars. We verified glycolaldehyde, some simple molecules with a sort of a peptide bond, some amides, carboxylic acids, and so forth. And so one, just looking at this list, could think of more complex species.
Before you go on, these percentages are based on the lines you've identified, or do they include the unknown lines?
The unknown lines, we don't know what they are, but
Right.
we'll, for example, we'll look at ethyl cyanide. We'll measure 200 transitions. We can model that for an abundance very accurately.
But what fraction of the lines are
Yeah.
unidentified?
Unidentified, about 30% right now. But usually they're the weaker lines. They're the weaker lines. Sorry?
That's all your U's in the...
Yes, I mean, there's a lot of U lines. Now, some of them may be due to some isotopically substituted species that no one really wants to study because it's boring, you know, like 15 substituted ethyl cyanide. I don't think it's been studied in the lab. Okay. But some of them are probably due to unknown species. And one interesting point here is that interstellar chemistry is not combinatorial. So if you have 5 carbons, 1 oxygen, and umpteen hydrogens to saturate the bond, you don't necessarily get all the combinations. You'll get one, but not the other. And why is that? Well, it's probably because most interstellar chemistry is not at equilibrium. It's kinetically controlled, so it's governed by rates. And so what gets made fastest hangs around, okay? The gas phase chemistry. The grain chemistry, That's a very complex subject. So we see these organic molecules in this cloud and in other clouds closer to our solar system, and you might say, well, okay, so all these molecules are out there. This has got nothing to do with the chemistry on Earth. But I don't think that's 100% true. Let's just look at one example. Recently, there's been the Rosetta mission. Rosetta was a spacecraft that was sent to a comet nucleus, comet 67P, and I won't bother to even try to pronounce that. And this is what that comet nucleus looked like. Very rugged terrain, and I think the lander landed somewhere here. This is a big object, okay, a couple kilometers wide. And when it landed, it kind of vaporized some of the surface. That's a sort of a cartoon of what it looked like when it was landed. And the material that it vaporized, it took a mass spectrum. And in that very interesting mass spectrum was what they think is this molecule, methyl isocyanate. We said, we haven't seen that in interstellar space. Is it out there? So once again, we had to go back to the laboratory because this is a horrible molecule for spectroscopy because we have a free methyl rotor. So this methyl group, this CH3, rotates around the molecular backbone, and then you have this NCO group, which is very floppy. And so the molecule is rotating, and this low vibrational mode is torquing the molecule, so it's not a very good rigid rotor. And that's what all spectroscopists like, are rigid rotors, right? Horrible, unrigid rotor. And there had been some laboratory work below 40 gigahertz. That wasn't enough for us because we couldn't extrapolate with the constants because the molecule's too floppy. And so we went and did our own measurements in the laboratory with the Fourier transform machine. Here are just some of the lab measurements at 86 gigahertz. We're really pushing our machine, so our U-shaped profiles are pretty asymmetric, but the measurements are fine. And we were able to measure enough lines to identify this molecule in our survey, which we had the data for. And so the black trace is all the molecules at different frequencies, all the spectral lines, and the red trace is our model of what the intensity and the frequency should look like, and everything matches up very consistently. 30 favorable transitions, we found all of them, no holes. And the interesting thing is the abundance in Sagittarius B2 is about a factor of 100 less than in the comet, but that's still pretty close considering all the approximations. In fact, that got us interested in comparing the abundances measured on the surface of the comet with those in our survey for various organic species. And so this is the ratio of the abundance in the cloud versus the comet. And a lot of these numbers are near 1 or 0.1, which is really pretty good agreement, except for carbon monoxide, which is so volatile one might not expect to see much in the comet. Okay? So that's interesting because comets, meteorites, dust particles condensed out of the molecular cloud that formed our solar system. And so comets like this are just remnants of interstellar material, and one might expect their abundances, which get frozen out because of the cold environments of interstellar space, to agree with a molecular cloud. We can't look at our molecular cloud in which we form because it's gone, but looking at something like Sagittarius B2 is representative. And the other interesting point is that the Earth went through a very heavy period of bombardment about 3.2 gigayears ago, and we know this from the moon record. And so a lot of organic material was delivered to Earth, a lot of it. And so one wonders, and the material came from comets, a lot of it from meteorites. People that study meteorites, even today, find a lot of interesting organic compounds in them. And so the question is, does interstellar chemistry at any level influence what's been delivered to Earth, and does what's been delivered to Earth exogenously influence how life started? And that's a big question. So one might wonder, and I'm almost done here, what other molecules are out there? I've mentioned C60, which is buckyball from a book, Buckminster Fullerene. That's its picture, 60 carbons in this nice cage structure. C60 plus as well, the ionized form of it, have been observed in some select sources, some planetary nebula, some clouds. They've been seen towards some signs of lines of sight in diffuse clouds. Radio astronomy can't claim this as their result. They were actually measured by their bending modes via infrared astronomy. These molecules have no permanent electric dipole moment, so they have no pure rotational spectrum, as they are pure C60. And so the interesting thing is you think of the list of molecules that we typically see in radio astronomy, and they typically have less than 13 atoms, and yet we make a huge quantum jump to something with 60 atoms. How does that happen? And what's in between? There's got to be a lot of molecules in between these sizes. So one can think of 10-membered carbon rings, which are actually, this one's asymmetric, so it has a permanent electric dipole moment, things with substituted oxygens into the carbon ring, and so forth. So there's many, many species one could think of that could be out in space that make the link between the more simple stuff and the very complicated things. Now, how buckyballs are made in space, it's a big question. In the lab, they're made by C2 units coming together, which is why we keep looking at the CCH molecule in planetary nebulae, because that may be a tracer of C2 and how it leads to C60. However, one could also find things, perhaps multi-carbon sugars, 5-carbon sugars, nitrogenous bases, maybe phosphate esters. We see a molecule with a phosphorus-oxygen bond. They could be out there. We just don't, usually we don't have the lab spectrum, and we have this confusion problem with these more complicated molecules. But it is interesting to note that when life formed on Earth, it was very selective in what materials it chose for starting materials. If you look at DNA and RNA, there is one sugar, ribose, deoxyribose, 5 carbons. People have done studies. A very famous chemist by the name of Eschenmoser at ETH in Zurich found out that other sugars work equally well in the DNA structure. You have 5 nucleobases, adenine, guanine, which links the phosphate esters. There are other nucleobases that can be used, have been used, experiments have been done. Why only 20 amino acids? There's hundreds of amino acids, okay? So the point here is it is likely that when life began on Earth, it just used what was available, and it worked. So that's what happened. So what happened was it's just a question of synthetic contingency, what was available. And the question is, did interstellar chemistry influence what was available on Earth to make life? That's one of the big, overwhelming questions if you're interested in the field of astrobiology. So, in conclusion, I think radio astronomy has really opened this field of interstellar astrochemistry, and it's really given us a new dimension of our notion of where molecules form, what molecules form. There's far more chemistry occurring out in interstellar space than on a planet, for example, when you really add everything up. I think another thing we've learned is the molecular material is far more common in our galaxy than ever imagined. And they're present under very harsh conditions. And there's probably more to be found. Another idea is that molecular material is recycled in the galaxy. We don't always go back to atoms as we go from source to source. And really the chemical lifetime, one might think, is the chemical lifetime of the galaxy, not an individual object. And we don't know the limit of the molecular complexity in the interstellar medium yet. We probably won't know for many decades, but our big challenges are working in the laboratory and doing the measurements we need, and the problem of line confusion in a spectrum. And we sort of need to work on the connections between what happens in our solar system and what happens in a molecular cloud and its influence on prebiotic chemistry. Unfortunately, there are many, many pieces in the puzzle, and only a few really have been assembled. When one thinks that the field of molecular line radio astronomy began in the early 1970s, it's not a very old field, and we have much to learn. And radio astronomy, I'm sure, will continue to play a major role in understanding and answering some of these questions. Thank you.
Very nice. Yeah. We have time for questions.
How do you, for the solar system stuff, how do you know if the chemicals were being processed in the disk?
Some of them are, right? But some of these things like comets, they were sort of, the protostellar disk formed, but there was debris that didn't make it into the protostellar disk. So that stuff didn't get heated up. It stayed on the outside of where the planets were forming. And then it got swept in. There was, things were moving around. And so one actually remembers that the solar system is present in the Oort cloud, right? And the Oort cloud is the debris of the molecular cloud the solar system formed, and the Oort cloud is huge relative to the solar system. So there's all this debris material, and occasionally it makes it into the solar system, or some of it was broken up planets, but a lot of this stuff got very cold very quickly and stayed cold. And yes, if you look in meteorites, they can distinguish between some meteorites that are really pristine and some meteorites that have aqueous processing. So yes, there is processing, okay? But we know it isn't all processed, and we know that because of isotope ratios. And people spend a lot of time studying isotope ratios in meteoritic material, and the isotope ratios are so skewed towards heavy deuterium enhancement, carbon-13 enhancement, nitrogen-15 enhancement. Those sorts of enhancements only can form at very low temperatures. We're talking about 30 Kelvin here, and they have to be frozen in. Because immediately when you start heating it up, you'll get exchange, and you'll lose your deuterium enhancement. So we know that some fraction of meteoritic material reflects what is present in the interstellar medium. With processing, yes, there's always some processing. So the question is, how much is processed? How much isn't? We don't know. People studied only a handful of meteorites. So.
Yeah, so I wanted to ask you more about one of my lab's favorite molecules, ALH+. I noticed in your metal molecule list, neutral ALH didn't make that list.
No.
But you're interested in looking for ALH+. So
Okay.
Is there some reason?
Neutral ALH lies in a difficult region of the spectrum to observe from the ground. So people did look with Herschel Space Telescope, and they didn't find it, but those sort of space missions, unless it was a booming line, they probably wouldn't have detected it. And you never know. Aluminum, ALH plus is basically protonated aluminum, okay? Recently they found protonated argon, ARH plus. So it could be that the protonated form is more abundant than the unprotonated form. I don't know, okay? Depends on the source.
But somehow ALH plus might make it through the atmospheric window in ways that ALH doesn't?
That could be too. That's what I was asking about the rotational constant. So, you know, what you really need is an intense ground-based search where you can really put a lot of time into it. Because aluminum isn't that abundant. It's about a few times 10 to the minus 6 relative to hydrogen, so.
Is the line confusion problem one that in principle could be solved just by collecting more and more and more spectra in the laboratory, or is there a fundamental sort of combinatorial problem?
The line confusion problem is, you know, what you see is what you get when you look in an interstellar source. It's always going to be there. Okay, now you can do, with ALMA, I'm sure you've heard all about ALMA, you can do some interferometry and maybe zero in on a smaller region, and maybe you'll lose some of the confusion because molecules might be existing in slightly different regions. And that's one way to get around the confusion problem, is higher spatial resolution. Our approach is to have so many lines that, you know, maybe 50% of your lines are contaminated by other molecules, but there's enough left over to see. And then you look at the relative intensities. And you know, all these molecules have patterns. And even asymmetric tops have patterns with their asymmetry components. And you can look for those patterns. Okay? Sometimes they'll be obscured by other molecules, but if you can get that distinct pattern with enough lines, you got it.
Question, what is the rate at which unidentified lines are being identified? I mean, it's been, you know, these lines have been around for a long, long time.
I
So
would
are
say
we
at a
making any progress?
No, people have made some progress. For example, one of the lines of FECN was actually an unidentified line from an ERAM survey. But, you know, how many people in the world are working in the laboratory on this stuff? A dozen maximum, so you can imagine that, you know, people are detecting unidentified lines, but it's at a slow rate. So.
I'm still bothered by rejecting all my high school chemistry.
Okay, this is
CN
not
is
not
valence-
chemistry in equilibrium, right?
Yeah, so that's the issue with it.
Right.
It's all based on kinetics and abundance of the species that are feeding the creation of given molecules. But if you have aluminum cyanide.
Right.
Okay, I expect AlCN 3, I think. Aluminum is valence 3.
Right, and actually, yes, if you look at aluminum compounds in the laboratory, things you can buy, you can get
I can buy
aluminum, you get trimethyl aluminum, right? You want 3 bonds to it.
Yeah, I
But,
can buy
okay,
that, yeah.
but this is interstellar chemistry, okay, where it's years between collisions, okay? You don't ever, and I should have talked about this, you don't ever have a third body. Okay, so in the lab, you always have a third body. And so, because you don't have a third body, you cannot have reactions with barriers, with activation barriers, typically. So you have to have reactions that have no barriers, okay, and are exothermic. So anything with a barrier typically won't go, all right? So now you're in a different realm of chemistry. You're out of equilibrium chemistry. And so what happens, for example, take the case of HCN. HCN is a metastable isomer, HNC, right? You rearrange the atoms, right? In space, sometimes...
That's known what order they're in.
Right, HCN's much more stable, yet out in interstellar space, you'll find HCN almost as abundant, HNC,
It's
the
available as
HCN, because what happens is that you have some formation mechanism and you form HNC, and it's up here in the energy diagram, and HCN is lower, but you formed it here and there's a barrier to convert HNC back to HCN. So it gets stuck in that local minimum, okay? Because you're dealing with chemistry at 10 Kelvin, right? 2 body collisions at 10 Kelvin. So it's a different realm, and perhaps I often think about this. There's more chemistry going out in space. Maybe the chemistry here on Earth is the exception rather than the rule.
But in space also you have cosmic rays.
Yes,
that
and
can
there's other
also-
shocks.
That can,
Yeah.
that can also enhance the abundances. So, I mean, can you actually have cosmic rays also in lab experiments? Some low energy particles that could also interact with gas?
I don't know how you get you could probably come up with some kind of source. I've never done that kind of thing.
I haven't produced cosmic rays.
Yeah, I haven't frozen cosmic rays.
Well, low energy.
But yeah,
low
yeah,
energy
you could
particles.
try.
I'm not ever bombarding a very low energy particles.
What would you use as a
I
source?
think the rate of cosmic ray
Yeah.
driven reactions is
But
I'm sure you could simulate it somehow.
but you also
But
have...
it does happen in space.
It does
though.
happen
So
in
this is
space, and
not-
you have this tremendous time factor too, right? We won't sit around for thousands of years for something to react, so unfortunately.
Okay, with this note, let's thank Lucy again for a wonderful talk.